Okay, welcome you all in this 12th lecture on metric spaces. And so far, we have discussed the definition of a metric space or a definition of metric, several examples, interior of a set, interior point, boundary of a set, boundary point, limit point, closure of a set, closed set, and so on. And we have seen several examples related to these concepts and also a large number of exercises. And several exercises we have already solved in the previous lectures. Some exercises are left for your revision. Now, today we will discuss the subspace. Subspace means if you have a set of a metric space, can we say that it is also a metric space? Or if a subset of a metric space can be converted into a metric space? So, suppose X is a metric space and Y is a subset of X. Then we may convert Y into a metric space. How? By restricting the distance function D to Y cross Y. In this way, each subset Y of X can be made a metric space in this way. So, here is Y is. On the other hand, we may be given two metric spaces XD and YD prime. If Y is a subset of X and D prime is the restriction of D, then this dy prime is a subspace of XD. So, we have the definition of the relative metric or the metric subspace. Now, the question is that why are we studying the subspace? Why we are going to introduce the notion of a subspace? The main thing is that we are introducing this because we have seen that if we are considering, for example, if you take the set of all real numbers, okay, set of all real numbers with the usual metric, and let us take here is x1, okay. So, this my set is x is equal to 0, 1. Then this set as a whole space with respect to the usual metric. Here usual metric is what? Usual metric is dxy is equal to mod of x minus y. With respect to the usual metric d on R, this set is not open. This set is not closed. But if we consider this set as a metric space, not as a subset of R, and the metric over X is defined in the same way as the usual metric, then this space is closed as well as open. Why it is closed as open? Because as we have mentioned that every whole space, so this we are treating as a whole space. So, as a whole space, it is closed as well as open. So, we need to identify the subspace and the whole space, and that's why we are studying. Now, here is what, say for example, you can look here is 0, we have seen that 0, 1 over 2, this. This set is an open set in this metric space with respect to this usual metric. but this set is not open with respect in R with respect to the usual metric. So that's why we are studying to clarify how we can find, how we can check whether the set is open in the subspace or in the whole space or not. So we can first introduce the definition of a restriction. So let XD be a metric space and Y be a subset of X. Okay. The relative metric dy on Y is the restriction of the metric function d on y cross y such that dy xx is equal to xy. In other words, because we have d xd, we have xd is our metric space, it means that d is a metric from x cross x to R, or I can write R plus. Okay, and we can take the restriction of this on the subset. Now we are taking y is a subset of x. So let us take the restriction of this. Okay, and restriction of this I am writing in this way over y cross y. Okay, so what does it mean? The restriction. Restriction means the value of the function. Okay, for all the point x, y, all the points in y cross y is same as the value of d on y cross y. That is to say, the value of the function dy at xy, and xy are in capital Y cross y. Okay, it is same as the value of d in x, the value of d at xy for xy in y cross y, not in x cross x. So this is the restriction of the metric. This way we can find, we can check the restriction of the metric. Okay. Now it is easy to see that the restriction function is a metric on x. So we can see that because this is equal to this one, and because this satisfies this, d is a metric, and so it will so dy will also satisfy all the properties which is satisfied by the d, and therefore because d is metric, so we can easily prove that dy is also a metric on y. So it is metric on y. So the y, the space y with this metric dy is called a metric subspace of the metric space xd. So y dy is called the metric subspace of the metric space xd. In other words, you can say that, so let xd and yd prime be metric spaces. Okay, xd and yd prime be metric spaces. We say that yd prime is a subspace, this is a subspace of this space, that is to say yd prime is a subspace of the metric space xd if y is a subset of x and d prime is the restriction of d on y. So y is a subset of x and d prime is the restriction of d on y cross y. So this way we can define the metric subspace or simply subspace of a metric space X. Now here is let us see some examples. Again, as usual, we start the examples from the R, set of all real numbers, with the usual metric. Usual metric means dxy is equal to mod of x minus y. Now, if y is equal to the closed interval 0, 1 or open closed interval 0, 1, closed interval open 0, 1 or open interval 0, 1, and we define dy xy is equal to mod of xy. So forget of this portion. Okay. Now you look here is with this one dy xy. So dy xy is what? So dy xy, only consider only this portion. Okay. If you consider only this portion, then you will see that this is what? This is nothing but it is the usual metric on R. So this is equal to usual metric on R dxy. Okay. So dxy is same as dy xy for all xy in y, and therefore this dy is a metric on these sets. Okay, and therefore y with this dy is a subspace of R with the usual metric d. Now with this one you will see that everything, the limit point, the closure, interior, everything will be changed. That we will see later. Similarly, let us take R with the usual metric, Q set of all rational numbers, and of course Q is a subset of R, and then we define dq from q cross q to R by dq xy is equal to mod of x minus y. But this is what? Mod of x minus y, it is the usual metric on R, which means that it is equal to dxy, so it is equal to dxy. It means that for all xy in Q, it means that dq is the restriction of this d, which is the usual metric on R, and Q is a subset of R, and therefore Q dq is a subspace of QRD. Now take another example. Let In the unit n cube, In the unit n cube be the set of all n tuples, okay, x1, x2, xn of real numbers such that xi lies between 0 and 1, okay, for all I runs from 1 to n. Now define DC, okay, define DC from In cross In to R by this one. DC xy is equal to maximum of xi minus yi. And now can you recall that what is this kind of metric? This we have seen, it is nothing but it is the max metric on Rn, or we can say that it is equal to d infinity metric on Rn. Okay, so it means that we can see that so this is d infinity metric on Rn. It means that dc is the restriction of d infinity, that is the max metric on Rn. So this In with respect to this dc is a subspace of Rn d infinity, where d infinity is the max metric on Rn, which is defined in this way we have seen. So this way we can define, we can see that the In is a subspace, okay, is a subspace of Rn with respect to the metric d infinity, not with respect to the usual metric. So keep in mind, this is very important. Here is this is the restriction of d infinity metric, this one, and therefore In IN DC is a subspace of IRN D infinity. Okay, take another example. So for other example, let us consider Sn. The n sphere be the set of all n plus 1 tuples, that is x1, x2, xn plus 1 of real numbers such that the square of all these tuples is equal to 1. Okay, and then you define ds from Sn cross Sn to R by dsxy is equal to I runs from 1 to n plus 1 xi minus yi whole square whole raised to the power 1 over 2. But this is what? This you remember that we have defined a metric D2 in this way. This is the metric we have defined in this metric in if it is Rn plus 1, then we have defined this metric on Rn plus 1, or up to n it is the metric on Rn. And therefore ds is the restriction of this metric on Rn. And so ds, this Sn with ds is a subspace of Rn plus 1 D2. So this way we can prove. Okay, take another example. Let A be the set of all n plus 1 tuples x1, x2, xn plus 1 of real numbers such that xn plus 1 is equal to 0. That is to say the last tuple is equal to 0. And then we define dA from A cross A to R by dAxy is equal to maximum of xi minus yi. So maximum of, just we have seen that it is the max metric on Rn. Okay, so this is the max metric on Rn. So this is so it means that dA is the restriction of D infinity matrix. Okay, just we have seen the D infinity matrix. So they are max matrix. So dA is the restriction of D infinity matrix on A cross A, where A is the set of all n plus 1 tuples, okay, of real numbers where the last xn plus 1 is equal to 0. And then you can see that then dA is the restriction of D infinity and A is a subset of Rn plus 1, okay, and so ADA is a subspace of Rn plus 1 D infinity. Here is okay, here is Rn plus 1, this is subset of Rn plus. So Rn plus 1 D infinity. So these are the examples of the subspaces of a metric space. And now you see that you cannot say that if you say, for example, if you are taking this metric, okay, or if you are considering dA and defining it this way, then we cannot say that ADA is a subspace of Rn plus 1 with respect to the usual metric. No. Because the restrictive metric, the metric on the subspace subset must be the restriction of the metric on the whole space. So if we consider, if we say that DA is the subspace of the space Rn plus 1 and with the usual metric, it would not be correct. Because dA is the restriction of the D infinity matrix, not the usual metric. So this is the very important fact here. Let us take another example. Okay. So for we are considering the set of all polynomials defined on the closed interval AB. So PAB, as we have defined earlier, we have seen that PAB, which is a set of all polynomials defined on AB. So PAB is a metric space with respect to the max metric. So max metric is defined in this way. Keep in mind, we have defined the max metric in this way, and this is a metric on this PAB is a metric. Okay, now I define DP from PAB cross PAB to R by this one. DPFG is equal to maximum of mod of Ft minus Gt, and maximum is taken over closed interval AB. Then this is nothing but it is equal to D infinity matrix on PAB. So this is equal to D infinity FG. So this is your infinity Fg. It means what? It means that the DP is the restriction of D infinity. DP is the restriction of D infinity. And of course, and this is what? This you can treat D infinity. This is D infinity is a metric on CAB. CAB means set of all continuous functions. And PAB is a subset of CAB. Okay, and D infinity is a metric on CAB. So you can say that the PAB with DP is a subspace of CAB with D infinity metric. Okay, so this you can say, because look here is PAB is a subset of CAB, and DP is the restriction of D infinity, and therefore PAB DP is the subspace of CAB. But PAB DP is not a subspace of CAB with metric D, and the metric D is defined as the integral from 0 to A, okay, or A to B, B to A, or A to B, f of t minus g of t dt. Okay, this is a subspace of this metric, but this is not a subspace of this metric, because here dp is the restriction of d infinity, but dp is not the restriction of this d. So you cannot say this one. Now we have a remark which says that if Y is a subspace of a metric space X, then a set which is open in Y may not be open in X. This is a very important term. So if Y is a subspace of a metric space, okay, then a set which is closed in Y may not be closed in X. How it is? Consider Y is equal to the closed interval 0, 1. Okay? We consider Y is equal to closed interval 0, 1. Then the set 0, 1 over 2 open. Here is open. Okay? This set is open in Y. This set is open in Y, but not in R. This set is not open in R with the usual metric. How it is? We will see later. We will see later that how we can see that how we can say that this set is open in Y, and this we will see later. But this set is not open, as you know that this set is not open in R with respect to the usual metric. Also, if we consider Y is equal to the open interval 0, 1, then the set 0, 1 over 2 half closed, here is closed. Then this set is closed in Y. This set is closed in Y, but it is not closed in R with respect to the usual metric. So this is not closed in R with respect to the usual metric. Now this we will see later. So before going to see the openness and the closeness of a subset of a subspace, the closeness and openness of a set in a subspace and in a whole space, let us see the meaning of the open sphere or closed sphere in the subspace. So for that we have a lemma. So we have the lemma which says that y dy be a sequence of metric space, be a subspace of a metric space xd, and A is an element of y and r is greater than 0, then the S prime A r is equal to y intersection S var A, where this is the open sphere in y with respect to this metric, and this is the open sphere in x with respect to the metric D. Okay. So this is the main key. Basically, this is the main key to go further to see the openness and closeness of a set in a subspace and in a metric space. And this we will see in our next talk. So I stop over here and we will see you in the next talk. Thank you very much.